So let's see, this chapter 7 Equilibria is about reversible reactions and dynamic equilibriums. So reversible reactions, you should expect the chemical equation will have this kind of arrow where they go forward and go backward. Okay, so you should see this kind of arrow for reversible reactions. So let's say if the reaction is this kind, so we call it irreversible reactions. So let's see the point here. Reversible reactions. Some reactions go to completion where the reactants are used up to form the products, and the reaction stops when all of the reactants are used up. So this kind of reaction is called irreversible reactions, where we use this type of arrow. So this is irreversible reactions, this kind of arrow. Now the next point, in reversible reactions, the products can react to reform the original reactants. So that means the products can form the reactants. That means the reaction can go backward. So to show a reversible reaction, two opposing half arrow are used. That means this kind of arrow. Then you see the example here. This is what we call the irreversible reactions. So we have only forward reactions. So this is hydrated copper 2 sulfate. You heat it up, then it becomes anhydrous copper 2 sulfate. The water come out. Okay, so this is the water of crystallization that we practiced before. Okay, now let's see here. This is the backward reactions. So where the anhydrous copper 2 sulfate react with 5 water molecules to form the crystal, and overall we put it in this way to show reversible reactions. Okay. Then dynamic equilibrium. So let's see what is this. Dynamic equilibrium, so what they said, in a dynamic equilibrium, the reactants and products are dynamic. That means they are constantly moving, and that is the meaning of dynamic. So since they are constantly moving, so you should expect them to collide with each other and reactions may happen. Okay, then in a dynamic equilibrium, the rate of the forward reactions is the same as the rate of the backward reaction in a closed system. Okay, so when they achieve equilibrium, that means forward and backwards are same speed, and because of same speed, so the concentration of the reactants and products is constant. So there is no change in concentration of the reactants and product because the forward and backward reaction are same. Okay, so now let's say for example, if I have A change to B, if they achieve dynamic equilibrium, so meaning that they are still have reactions here, so A is still changing to B and B is still changing to A, they are still dynamic. And the thing is, the rates of forward and the rate of backward reactions are same rate until there is no change in concentrations of A and no change in concentration of B. Okay, so let's see this diagram here. We have hydrogen and iodine, so you can see this is H2 and this is I2, then they react to form HI. Okay, so of course the equation is going to be like this: H2 plus I2, then it becomes 2HI. Okay, so something like this. It is reversible, that's first thing, because of this arrow. The second thing is when they achieve dynamic equilibrium, so you should expect the amount of H2I2 in terms of concentration is constant, and then the amount of HI is also having the same concentration. Okay, so that's why you can see the diagram show a snapshot of a dynamic equilibrium. in which molecules of hydrogen iodide are breaking down to hydrogens and iodine at the same rate as hydrogen and iodine molecules are reacting together to form hydrogen iodide. So they are trying to say the forward and the backwards are same rate. Okay, so let's move on. Okay, now we have to start looking at the graph. This kind of graph is for reversible reaction. Okay, first let's start from the green lines. So this represent the reactant, the concentration of reactants. So the concentration of reactants will achieve equilibrium when the graph is horizontal. This is where it achieves equilibrium. So the idea of equilibrium is the concentration remain constant. Okay? So it doesn't go to zero. If the reactant's concentration goes to zero, that is irreversible reactions. So you have to know that. So if it just become constant at a particular value, but the product, you have to remember that product start from zero. Product start from zero, and when equilibrium reach, it becomes horizontal. So basically they reach equilibrium at the same time. Okay, you can see that. So it becomes horizontal at the same time. Okay. Then this is the second kind of graph. So sometimes so again you need to know this is the one that go down, right? Is basically it's normally the reactant. So let's see what they say here. Line shows decrease in concentrations of product as some product react to reform the reactants until equilibrium is reached and the concentration remain constant. Oh, so this is like the backward reaction. So backward reaction where the product change to reactants and hence the concentration decreases. And this is the reactants. The reactants is increasing. Initially there is no reactants, so the backward reaction causes the reactants to form and achieve equilibrium. Okay, so this is backward. This one is forward. Forward will be like this, where the reactant decreases. Okay, so the top one is forward reactions. Reactant decreases, products increases. Okay, so two type of situation here, two type of graphs. And let's move on. Okay, so just now they mentioned a closed system also, if you still remember. When we talk about the dynamic equilibrium, they talk about closed system. So here is the explanation. A closed system is one in which none of the reactants or product escape from the reaction mixture. So something like this. So they cannot go out from the container, for example. Okay, so in an open system, matter and energy can be lost to the surrounding, something like this. This is open system. So the substance or the matter can go out from the container. So when a reaction takes place entirely in solution, equilibrium can be reached in open flask as a negligible amount of material is lost through evaporation. Okay, if the reaction involves gases, equilibrium can only be reached in a closed system. So they are trying to tell you two situations. If the reaction takes place in solution, equilibrium, equilibrium must happen in a closed system. So equilibrium can happen in an open flask because the solution does not evaporate. Okay, so but if the reaction involves gas, equilibrium happens in a closed container. You must use a closed container, or else the gas escapes from the container. Then that is open system already. Yeah, so okay, these are the two diagrams. The first one shows the closed system, the second one shows the open system. Okay, now let's move on with the exam tips. Okay, so for this exam tips here, a common misconception is to think that the concentration of the reactants and products are equal. They are not equal, they are constant. If you still remember the graph just now, the graph just now where they put like the concentration of reactant, they put like this, then the concentration of product, they put like that. So you can easily see that they are not same one. Their concentration are not same. Concentration of product, concentration of reactants are not same. So if you think it is equal, then wrong concept already. So however, they are not equal, but they remain constant at dynamic equilibrium. So they remain constant, but maybe and most of the time it's not same one. So unless you adjust the concentrations purposely until they are same. So in normal situation they are not same. So the concentration will change as the reactions progresses, and only until the equilibrium is reached. So that the concentration keep decreasing for the reactant, the concentration keep increasing for the products until equilibrium. It become constant. Okay, now we have finished up the first part, which talk about dynamic equilibrium. So make sure you remember a few important key points for dynamic equilibrium. So dynamic means that the reactants are the substance are still reacting, are still moving. Okay, so the second thing is equilibrium means they have the same they have the constant concentration. And the third thing is the equilibrium happen in a closed system. So basically these are the important points. So now we look at Le Chatelier principle. So they are talking about what happened during equilibrium. So this principle is talking about what happened during equilibrium. But let's see something before it, before the principle. So it's about position of the equilibrium. So the position of the equilibrium refers to the relative amounts of products and reactants in an equilibrium mixture. Okay, so for example, let's say I have A which reacts and become B. So if I have more product, then I say positions to the right. If I have more product than reactants, then the position of the equilibrium is to the right. So if let's say during equilibrium, if I have more reactants compared to products, then I say that the position of the equilibrium is to the left. So it depends on the relative amount. So you have to compare between this and this. Whoever that is more, that means the position is at that side. Okay, let's say example, when the position of equilibrium shift to the left, that means more reactants. It means the concentration of reactants increases. When the position of equilibrium shifts to the right, it means the concentration of product increases. So right means more products. And Le Chatelier's principle says that if a change is made to a system at dynamic equilibrium, so you have to know that they achieve equilibrium already, they achieve dynamic equilibrium, and you go and change it. So you change the equilibrium. So the position of the equilibrium moves to minimize this change. So that is the principle. Okay, so there are three stages basically. First, the system is under dynamic equilibrium. Second, you go and change the you go and do some change to the system. And then the system means the substance will react in a way to minimize the change. minimize the change. So that they need to shift to a particular position, either to the left or to the right, to minimize the change. Okay, so let's say example, if I have A and B that are under dynamic equilibrium. Okay, so this is the first step. It is in equilibrium now, and you go and increase the amount of A. Okay, you just add more A to the solution, for example. Okay, so after that, based on Le Chatelier's principle, the positions of equilibrium will shift to the, okay, so let me ask you, will shift to the left or shift to the right for this case? If I increase A.
If you increase A,
Yeah.
Would it shift to the right?
Yes, correct. It will shift to the right. It will shift to the right so that it minimizes the change. That means when it shifts to the right, then this amount, this A does not increase that much. Minimize the change. So position will shift to the right. Okay, so 3 stages basically. Okay, now let's continue. Next point, the principle is used to predict changes to the position of equilibrium when there are changes in temperature, pressure, or concentration. Basically 3 changes. So you can change the temperature. How it affects, we'll discuss in detail later. It depends on endothermic and exothermic. You can change the pressure. This we will discuss in detail also. It depends on number of mole. Concentration, I already discussed a little bit here, where I increase the concentration of A, then it shifts to the right to minimize the increase of concentration. Okay, so let's continue. Okay, this is the first one. Effects of concentration. Okay, so first, let's look at the effects of concentration table here. So what happens is you increase concentration, increase in concentration of the reactant, let's say. Okay, the reactant. I add in this one. Increase in concentration of reactants. Like the example that I put just now. I increase A, then you say it shift to the right. Okay, so equilibrium shift to the right to reduce the effect of increase in the concentration of a reactant. So this is what we discussed. This is Le Chatelier principle actually. If you decrease in concentration of reactant, okay, so then the equilibrium shift to the left to reduce the effect of a decrease in reactant or an increase in the concentration of products. Okay, so that means if you increase the concentration of product, it shifts to the left also. So there are 2 situations which make it shift to the left. So either you decrease the concentration of reactant, then it shifts to the left. If you increase the concentration of product, it shifts to the left also. Okay, now let's see this one. Okay, so this one we discuss straight away. Use the reactions below. Okay, this is the reaction. Ethanoic acid plus ethanol become this. This is an ester. This ester is called ethyl ethanoate plus water. So explain what happens to the position of equilibrium when more CH3COOC2H5 is added. Okay, so that means this one. So you have to decide now whether, since they are asking position of equilibrium, so you just need to say either the shift to the left or shift to the right. So you have to decide on that. So what do you think? Shift to the left or right?
Does it shift to the left?
Yes, correct. So it shifts to the left. Okay, so of course, how to explain? You have to explain based on Le Chatelier principle, something like it shifts to the left to minimize the increase of the concentration of the ester. To minimize the change, basically. That's the keyword. Okay, so number 2, some ethanol is removed. Okay, you remove this one. Now you have to decide whether the position will shift to the left or shift to the right. So what do you think?
To the left?
Yes, correct, to the left. Okay, so it's correct. It shifts to the left so that they form the ethanol and minimize the decrease in the concentration of ethanol. So you see, the explanation is always talk about to minimize the change. Okay, so we are playing around in that keyword. Okay, now use the reaction below. Okay, this is the reaction. Explain what happens to the position of equilibrium when water is added to the equilibrium mixture. Okay, so you think about it. What do you think? What will happen?
I was thinking that
Yeah,
it will either move to the left or there will be no change.
move to the left or no change. Okay, why you think like that? Any?
Does adding water to equilibrium mixture mean that they just add it to the reagent, or is it like just the whole thing?
The whole thing actually. So you imagine your container contains 4 of these things. Your container contains Ce4 plus, Fe2 2 plus, and Ce3 plus, and Fe3 plus. So you add water to it.
Then I think I would say no change.
Yes, okay. So it is no change. So there is no effect because the water dilutes all the ions. Water dilutes all the ions. And when it dilutes all the ions, so of course at the end they are all become more dilute in the same ratio basically. Okay, so no change. Okay, so the positions of equilibrium will change if you dilute one of it. Let's say for example you remove this one, then the concentration of these, only these decrease, and then the equilibrium will shift to the left. But if you decrease the concentration of all of these, then no change in the position. Okay, let's move on. Effect of pressure. Okay, so this is for gas actually. So as you can see here, changes in pressure only affect reactions where the reactants or products are gases. Okay, for gas. This now is concentration, right? Concentration is for solutions normally, but even for gas it works also. Okay, but for pressure, this is for gas only. Okay, now let's see the change, the effect. If you increase in pressure, okay, so let's say I put one example here. Okay, I put one example. Let's say I have 2A changed to 3B. Okay, so the reaction happened in this way. 2 mole of A reacts to form 3 mole of B. Okay, now you increase in pressure. So imagine that these two are gases. They are in the same container. Now you increase the pressure. Okay, so equilibrium shift in the directions. What direction? Not fixed. It depends on equation. In the direction that produces the smaller number of molecules of gas to decrease the pressure again. You know, they want to minimize the change, right? So if you increase it, they try to minimize the change by decreasing the pressure. And how they decrease? They shift to the direction that decrease the number of molecules. Yes.
So for this like pressure, will they ever give a reversible reaction that has both a gas and like a solid or aqueous substance?
Yes, it is possible.
So in that case, do we ignore like the aqueous or solid because it's not a gas?
Yes, we have to ignore that. We just look at the gas. Let's say for example, this one. So for this case, number 2, right? So left hand side consider no gas, right hand side consider 1 mole of gas. So it's 0 and 1. This one you ignore. So solid we ignore. So 1 mole, 0 to 1. So if you increase in pressure, then they will shift to the direction with smaller number of molecules, that is from 1 mole to 0 mole. So something like that. Okay. And if let's say this is my case, if you increase in pressure, so it shifts to the left or shift to the right? What do you think?
To the left?
Yes, correct. It shifts to the left. When you increase in pressure, it shifts to the left because left hand side has less number of mole. Okay, so when the mole decrease, then the pressure decrease. So that change, that minimize the effect of increasing the pressure. So now the next one, decrease in pressure. Equilibrium shift in the direction that produces the larger number of molecules of gas to increase the pressure again. So that means you decrease in pressure, then the equilibrium will shift to the right. Then the number of mole increases, and then the pressure increase. That minimize the change of this. Okay, so they are like trying to balance back whatever happens. Okay, now let's discuss this straight away. Predict the effect of increasing the pressure on the following reactions. So when you predict, right, you just need to say the position shift to the left or shift to the right. Okay, so now let's try number 1. So what do you think for this? Shift to the left or shift to the right?
To the left?
Yes, correct. Shift to the left. Okay, so of course if they ask you to explain, you just say because left hand side has fewer gas molecules. Okay, now number 2. What do you think when you increase the pressure? Left or right?
The left again?
Yes, it shifts to the left. So like what we said, we don't care about the solid, we just care about the gas. So 1 mole of gas here, 0 mole of gas on the left. So from right to left. Okay, predict the effect of decreasing the pressure on the following reactions. Okay, so you need to decide again, shift to the left or shift to the right.
Increasing pressure. So would it move to the right this time because the right side has more moles?
Yes, correct. It moved to the right. More moles on the right. Okay, so you understand the concept here. Okay, now let's look at the third factor. Effect of temperature. Okay, so we look at the table. If you increase in temperature, so this time, right, the equations have to involve the delta H at the same time. Let's say you have let's say you have A become B, then they give you delta H equal to positive X kilojoule per mole. So they have to give you the delta H, the enthalpy change, so that you know whether it is endothermic or exothermic. So when I give you positive X, I hope you still remember this is endothermic. Okay, so and I have to say that it is endothermic when it is forward reactions. Okay, forward reaction is endo,
Yeah.
and backward reaction is exo. So this is the delta H given is always referred to forward reaction. Forward reaction is endo, and backward is exothermic. Okay, so now let's see the table again. If you increase in temperature, the equilibrium move in the endothermic direction to reverse the change. So of course they move to endothermic because endothermic absorbs heat. So if you increase the temperature, then they absorb back the heat so that the increase is minimized. So the increase in temperature is minimized. So something like that will happen. Okay, now let's say if I increase in temperature, for my example here, the position will shift to the left or right.
To the right.
Yes, to the right. Okay, to the right, because right hand side is endothermic. Okay, so decrease in temperature, equilibrium move in the exothermic direction to reverse the change. So that means shift to the direction that causes exothermic, and exothermic releases heat to the surroundings to compensate the decrease in temperature, to heat up the surrounding, so it minimize the change here, so let's see example here. Okay, now let us discuss this straight away. Use the reaction below, H2 plus CO2 plus this equal to, delta H equal to this, endothermic. Predict the effect of increasing the temperature on this reaction. Okay, so you just need to determine whether it shifts to the left or right. So what do you think?
To the right.
Yes, correct, to the right. So if explanation is required, you just say because forward reaction is endothermic, which absorb the excess energy. Okay, so you can just explain something in that way lah. The keyword is endothermic. So okay, now let's see. Use the reactions below. Okay, this is the reaction, and increasing the temperature increases the amount of CO2 at constant pressure. Okay, so try to imagine. Is this reaction exothermic or endothermic? Okay, so you determine this first. Endo or exo?
Is it endo?
Yes, it is endo. Okay, so of course, when you increase in temperature, what happens is endo is going to happen. So when they say amount of CO2 increase, that means it is going to shift to the right. Okay, so that means delta H is positive. That's positive. Okay, so when you want to explain, so basically you have to focus on a few keywords. So the first keyword is endothermic. Endothermic. Okay, so after that you have to say absorbed energy. Absorb energy. So something like you say it is endothermic because it absorbs energy when the temperature is increasing. So let's move on. The next one, effect of catalyst. Okay, so a catalyst is a substance that increases the rate of a chemical reactions. They increase the rates of the forward and reverse reactions equally. So the statement in bracket is very critical here. Okay, so it makes the reaction fast. So they are trying to say something like that. But at the same time, they put one additional note saying that it makes the forward reaction and backward reaction faster in the same rate. Okay, so catalysts only cause a reaction to reach its equilibrium faster. Catalysts therefore have no effect on the position of the equilibrium once this is reached. So you should expect something like when you add catalyst, you don't expect the position will shift to the left or shift to the right. Okay, no change in the position. Something similar to you add water to the system just now, involving four aqueous, 4 ions in aqueous. So no effect also. Okay, so catalyst similar. So you add catalyst, no effect on the position. So what happens to catalyst is catalyst will make equilibrium to be reached faster. Okay, but position is not affected. Okay, so let's move on. Okay, so we finish up the theory part, which is the Le Chatelier principle. Now we start the calculation part. Okay, so this is the starting of the calculation part. So we have equilibrium constants for concentrations. Okay, concentration. So which is Kc. Kc stands for concentration, equilibrium constants. Okay, so what is Kc is a formula for calculation. Okay, so equilibrium expression and constant. So first point, the equilibrium expression is an expression that links the equilibrium constant Kc to the concentration of reactants and products at equilibrium, taking the stoichiometry of the equation into account. So you see this is the equation, and Kc is formed in this way. You take the products C and D, take their concentration, that's why you put in square bracket, and then you have to raise to the power of the number here and here. So that's why you have small letter C and small letter D there. That represent the number in front of the products. And at the denominator, we put the concentrations of the reactants and raise to the power of A and B. Okay, so that is the formula for Kc, and everything is in concentrations, so that means you should expect the unit to be mole per dm cube. Okay, so as you can see here, the concentration is in the unit of mole per dm cube, and imagine concentration is mole per dm cube, then you have a power C over there, so you have to times power C. Okay, so this concentration have to raise to power C, and then concentration again raised to power D. So that means you should expect at the end the concentration at the numerator is raised to the power of C plus D. For the denominator, the concentrations mole per dm cube is raised to the power of A plus B. Now since the numerator and the denominator are dividing over there, so at the end you should expect the concentrations is going to be C plus D minus A minus B. Okay, so because when you divide, right, you need to minus the power. So at the end, you get concentration with this power. That is the unit for Kc, which is not fixed one. It depends on equation, depends on the A, B, C, D in the chemical equations that affect the units of Kc. So we should expect sometimes it has no unit also when C plus D minus A minus B equal to 0, and then there is no unit. Okay, now let's see more. Solid are ignored in equilibrium expressions, so that means if any of these are solid, no need to put them in the formula. The Kc of a reaction is specific and only changes if the temperature of the reaction changes. So that means Kc is always a constant until you change the temperature. So for example, right, let's say this system is in equilibrium now. Then you put the concentration, when they are equilibrium, the concentration are constant. And then you put a constant concentration over here, then you get your Kc. So once you get your Kc, right, so you can disturb the equilibrium. Let's say you add more reactant A to disturb the equilibrium. You increase the concentration of A. So remember, if you increase the concentration of A, it doesn't affect the value of Kc because only temperature can change the Kc value. So if you increase the concentration of A, then the Kc remain the same value as what we established before. Okay, we have the same Kc. You increase the concentration, and then you can do calculation to find out, when you increase this, then at the end position will shift to the right, and then you can find a new concentration of C and D, and a new concentration of B, and a new concentration of A as well. You can count that because Kc is constant. Okay, so
Wait, so
yeah.
it says solids are ignored in equilibrium expressions. So does that mean if it's in the reaction, we just ignore it?
Yeah, we ignore it. For example, like let's say you have displacement reaction, zinc solid plus Cu2 plus aqueous become, okay, let's say it become zinc 2 plus Cu solid. Okay, so in this situation, we don't care about the solid. And when we don't care about the solid, when you want to write down the Kc formula, then we just write like this. Kc equal to the concentration of the product, which is zinc 2 plus, raised to the power of 1, because here is nothing, so 1, and then divide by the concentration of Cu2 plus, this is on the reactant side, and raised to the power of 1 as well, as there is no number here. So you can see we don't care about the solid in this case. Okay, now let's move on. Okay, so we have a question here. You take a try first. So I just write down your answer. So make sure you put the square bracket. Okay, how about number 2? What is the formula?
NH3 squared over N2 times H2 that is cubed.
Okay. Yeah, correct.
The unit is mole negative 2, and then DM6?
Yes, correct. Okay, how about number 3?
SO3 cubed. Sorry, squared.
Squared, yes.
And then SO2 squared times O2.
Okay.
And then the unit would be mole negative 1 DM3.
Okay, yes. Okay, so yeah, correct. Let's move on. Okay, so this is mole fraction and partial pressure. So let's go through. Okay, so we start from partial pressure. Okay, so what is partial pressure? You look at the picture first. So let's say in a container, we have mixtures of gas. So where you can see the green dots here are the gas A, and then we have blue dots that represent gas B. So we have the mixtures of gas. So if you connect these to, let's say, to a device that measure pressure, so basically you are getting the total pressure. So you get the total pressure if you go and find out the pressure of the container here. You get the total pressure. But you have to know that the total pressure is the pressure of gas A and gas B. So there are two gases that contribute to the total pressure of 11 Pascal. And when you see it individually, the pressure of gas A, which is 8 Pascal, And this is the idea of partial pressure. Okay, is the pressure by one types of gas, that is partial pressure. Okay, then this is the partial pressure for gas B. So again, we use the words partial pressure to represent another types of gas. Okay, so that's the idea of partial pressure. Okay, now for reactions involving mixtures of gases, so you have a mixtures of gases, the equilibrium constant Kp is used. Kp is for pressure. Just now Kc is concentration, this is pressure. Kp is used as it is easier to measure the pressure than the concentrations for gases. So Kp is for gases. Kc is for gas or solution, not for solid. Okay, so the partial pressures of a gas is the pressure that the gas would have if it was in the container all by itself. So in other words, it's the individual pressure. So the partial pressure is by the individual gas. So the total pressure is the sum of the partial pressure. So you have to total up the partial pressure to get the total pressure. Okay, so this is an example involving three types of gases. Then you total up the three partial pressure of the gases. Then you get the total pressure. Okay, now let's see the next page. Okay, so when you want to do partial pressure, we need to use mole fractions, because later partial pressure is equal to mole fraction times total pressure. So that's why we need to learn what is mole fraction. So the mole fraction of a gas is the ratio of moles of a particular gas to the total number of moles of gas present. Okay, so let's say for example, okay, let's say in a container you have 2 mole of gas A and you have 3 mole of gas B. Okay, so if you want to find the mole fraction of A, so we just take gas A, which is 2 mole, divide by total number of moles, which is 2 plus 3, and you get 2 over 5. So mole fractions of B, then the B stay at the denominator. The number of moles of gas B is on the denominator, which is 3 mole, and at the bottom is always the total, 3 over 5 then. So this is the idea of mole fractions. So after you get the mole fractions, then we can find out the partial pressure of each gas by using this formula. We can easily know the total pressure because you can just easily channel this to a device, to an instrument to measure the pressure, like barometer or manometer to measure the pressure. Okay, so you measure the pressure and that is the total pressure. Then you multiply with 2 over 5, then you get the partial pressure of gas A based on this formula. And you take total pressure, multiply with 3 over 5, then you get the partial pressure of gas B. Okay, so they follow ratio basically. The partial pressure follow the ratio of gas A and gas B. Okay, so if the mole is greater, then the pressure is greater. If the mole is smaller, then the partial pressure will be smaller. Okay, then let's see here. The sum of the mole fraction should add up to 1, while the sum of the partial pressure should add up to the total pressure. Okay, so logically this is true, as you can see. 2 over 5 plus 3 over 5, you add up to 1. That's the sum of the mole fraction. And if you add up the partial pressure of gas A and partial pressure of gas B, then you get the total pressure. Okay, now let's see the next subtopic. Equilibrium constants, partial pressure, that means Kp. So equilibrium expression involving partial pressures. So equilibrium expression in terms of partial pressure are written similarly to those involving concentration with a few differences. Okay, let's see the differences. Okay, you can see here. Kp, we use partial pressure of gas C to the power of C, partial pressure of gas D to the power of D. This one, you can see they use square bracket to represent the concentration. Okay, so again, at the denominator, they are using partial pressure. This one, they are using concentration. So that's the difference. Okay, so let's find out the formula for Kp then. So we discuss this straight away. You can just set it out. I will check straight away. What is the formula for the first one?
So would we write it as like PNH3 all squared?
Okay, yes, correct. Divide by?
And then PN2 times PH2 cubed.
Yes, correct. Cube. Okay, so if let's say we want to find out the units of Kp, so what will it be? They are using Pascal, by the way. Yeah.
Do we use pascals?
Yeah.
-2?
Yeah, it's correct. Okay, question 2. What is the formula for Kp?
PNO2 squared
Okay.
over N2O4. PNO2 N2O4.
Okay, yes, correct. So what is the unit?
Just pascals.
Okay, yes, correct. Question 3. Formula?
PSO3 squared over PSO2 squared times PO2.
Okay, yes, correct. What is the unit?
Pascal -1.
Okay, yes, correct. Now let's move on. Okay. Equilibrium constant calculation. Okay, so calculation involving Kc. In the equilibrium expression, each figure within a square bracket represents the concentration in mole per dm cube. This one we discussed already. The units of Kc therefore depends on the form of the equilibrium expression. So the unit of Kc, I think you know well. Just need to simplify the power. Okay. Some question give the number of moles of each of the reactants and products at equilibrium together with the volume of the reaction mixture. So why they need to give mole and volume? Because you want to find concentration, right? So that's why the question have to give you mole and volume, so that mole divide by volume and you get concentration. Okay, so the concentrations can be calculated from the number of mole divided by the total volume. Okay, so the formula is like this. So we need to find out the concentration, then we can put into the expression of Kc. Okay, now this one. Okay, so you try first. So first of all, let us write down the formula for Kc first. What is your formula for Kc then?
H2O times
H2O.
CH3COOOC 2H5.
Okay.
over CH3COOH times C2H5OH.
Okay, yeah, so this is the formula. The formula is correct. Okay, what value you substitute for the concentration of the first one, let's say H2O?
I did 0.182 divided by 0.5.
Okay, yes, that's correct. So what value you substitute for this?
That one I did 0.182 over 0.5 as well.
Okay, then how about this one?
0.235 over 0.5.
And finally, how about this?
0.0350 over 0.5.
Oh, okay, so everything is correct. Supposed to get the answer. Let me try to press calculator to double check. So just now you said what value again?
I got 0.890, but maybe I typed something
Oh,
wrong.
okay. Yeah, there's something wrong. You may type again.
4.03.
Yes, and no unit. Okay, so it's
Yeah.
correct now. Okay, so of course, if I'm doing right, I will just cut the 0.5 away, because they are just nice to cancel off. Okay, this cancel with this, and I mean this one cancel with this one, and this one cancel with this one. Then I can just easily key in 4 values in my calculator and get this.